I really like those influences, like strictness, declarative, explode early, because if you think about your problem at the start, this will save you a lot of time and a lot of headaches later. We came up with the expression API, which are very small building blocks of operations which can be chained. And every expression can be combined with another expression, and you can do this indefinitely. And by the combinatorial explosion of things you can combine, you get a very powerful API, and you can do a lot of things with expressions, Polars expressions, without ever needing a Python Lambda. And this has a lot of benefit.
In this episode of Inspiring Computing, we talk to Richie, who is the author of Polars. Polars is a Python package written in Rust, and anyone who has ever used pandas will for sure find this episode interesting. As Polars has incredible speedups compared to pandas, but in order to do so, it is interesting to hear from Richie where he got his inspiration from, how did he go about creating such a powerful package, and where is he actually going in the future. In this episode, he talks about some of the optimizations that he implemented.
Welcome to Inspiring Computing. This podcast is where computing meets the real world. This podcast aims to trigger your curiosity by talking to proficient and advanced users of MATLAB, Python, and Julia, who use these tools to deepen their understanding of the world by simulating it, exploring trade-offs, and gaining insights that help their companies add more value. In addition to proficient users, we will be also talking to product marketing, toolbox authors, package developers, and library maintainers to see what drives the development and what issues they're solving for others to benefit from.
Welcome, Richie, to Inspiring Computing. I actually heard of you at a PyData Eindhoven conference where this gentleman, Harizo, spoke about the overview of all the DataFrame frameworks, and Polars came up, and then I heard of your name. I'm very grateful to have you on the show. So welcome, Richie.
Hi.
So you are the author of Polars. But before we get into what exactly Polars is as a data frame, I did a bit of looking on your personal LinkedIn, and I saw you actually trained as a civil engineer. So tell me a little bit about how does a civil engineer go from becoming a civil engineer to creating one of the most popular data frame libraries on the planet? Tell me the story behind that.
Yeah, it's a bit like a meandering river. You don't really know what you want to do when you're young. I think that's the gist of it. I made some bad choices when I was younger, ended up working in physical work, physical labor. I was actually a street paver. I've been doing that for 5 years or so, and then picked up my life a bit better. I started studying civil engineering because that was mostly related to the physical work I did. So that was the thought that got into that. Anyway, I became a civil engineer, structural engineer. As a structural engineer, you calculate the mechanics of equilibrium, the equilibriums of bridges, of houses, of structural integrities. And I did this kind of work for 4 years, and I was always hacking a bit around with Excel, and I liked algorithms already, but I wasn't really proficient in programming whatsoever. But a friend of mine was, and he told me to start doing Codecademy with Python. And I started doing this one Sunday afternoon, and I got hooked. I really liked it. I really loved it. So I would say I got addicted to programming. My girlfriend didn't like it at the time. So I finished that course, and then I started trying to do some computations, some calculations. I did a work with Python, and one thing got to another, and I started automating my day job. Actually, there was a lot of repetitive work, and we needed to make models in a computer, which came from a drawing. And long story short, I automated that. And the more I did, I think in 1.5 years, my work became more as that of a structural engineer to more of a budding software engineer. And eventually I grew a bit out of that company because people didn't really understand. They felt like you're playing around when like the management liked it because it saved a lot of money, but your colleagues they think you're playing around, you're goofing around. So there's a thing called finite element calculations where people make models, and those models need to be built. And in the old process, there was someone who had a master's degree would take in a drawing of the model and then take that drawing that was made in a computer, take that drawing to paper and fill in the dimensions in another program. That's insane, right? So you take something out of the computer on paper and back into the computer. And what I did there was, okay, making sure we can export that model to in that time we used XML for that, to an XML file, and then import that other model. It was all a bit hacky, like hacking around. It saved a week of manual labor, like manual and other stuff. But yeah, the civil engineering world is quite traditional. The colleagues felt more like you're playing around. And I got interested in data science and been dabbing into that. And then I started working as a data scientist after that. And then the ball kept rolling. Did some consultancy, did data engineering, and later software engineering. I've been doing that for 5 years or so. Yeah. I think the overarching theme there was that I always wanted a new challenge. And in data science, I really could find a challenge for a while. There are a lot of algorithms, there's a lot of models to understand, a lot of linear algebra. So I really liked that world, got interested in Bayesian statistics, and been doing a lot of projects on the side. I really like blogging then. Yeah, data science piqued my interest for a couple of years, but I did consultancy. But I felt that at clients, it became a bit of the same story often. Especially in the beginning, there was the AI hype. I felt everything needed to be in machine learning, where I often felt like rule-based, common sense software engineering was much better. And
quicker, faster, and
faster, you have control. So I often felt like common sense went out of the window. And we were often in teams with, I don't know, like 5 data scientists and 1 data engineer, where I think it should be reversed. And then you were like months trying to make a model better, getting it 1 or 2% better in accuracy. And in the end, it's not used, it doesn't get to production. I experienced a lot of client cases where it was like this. So I went more into data engineering, which I found to have more utility. And I joined another company during the time, a startup as a partner, as a software engineer. We made software engineering tools for the civil engineering field. Yeah.
So you went back to your origins. And then you decided to create Polars, right? So how did the idea of Polars come about? Was it when you were as a consultant and in this startup that you realized everyone was using pandas and you got frustrated?
No.
Or what was it?
So during all the time I started programming, I started doing side projects. From the beginning, I always did side projects and I built all kinds of stuff, all kinds of algorithms. And my latest project was Polars. I was very excited about the Rust language, and I've been playing with that one for a while. And during COVID, I learned about Arrow, the Arrow project, which I also got excited about. And I recall that I was writing a backend in Rust, and I wanted to read some data from this CSV file, and I needed to join it with another file. And this was much harder than I anticipated because there wasn't a DataFrame library, or I had to bring in a SQL backend, and I thought, okay, maybe I can write something myself just for the needs I have. That's how I started. Maybe I can write a small DataFrame utility just for the needs I had. And so I wrote a join algorithm, and naturally you start comparing, okay, how well did I do? So I compared it with pandas, and my initial implementation was terribly slow. As a fun project, I thought, let's make it faster than pandas. Actually, it's the story of changing goals with what you build continuously. Initially, I just started, maybe we can make this small. And later I thought maybe we can make this a DataFrame library only for the Rust language. And now maybe we can make this a DataFrame library that's very popular in Python. Currently, the goal is maybe we can make a DataFrame library that scales to huge data sets on your machine.
Interesting. Yeah. So Polars itself, right? This is programmed in Rust. This started as a side project, so it wasn't necessarily something that you did in your day job. And you had a curiosity, and I think many open source projects start as you have a question, you want to solve it yourself. You couldn't quite find the right tool. Smart person, I'll make my own. And then, okay, you want it to be better than state of the art, and then you end up sharing it, right? But then it grows from there, right? And how popular is actually Polars now? I saw on GitHub, you've got something like 14,000 stars, and I see conferences, talks all about Polars. So it kind of exploded or gone viral, so to say. So how did you do that, Richie? Was that ever the intent, or was it just, no, I just want something to be cool. I like Arrow project. I want to build on it. Rust is a cool technology, and let's see how far I can go. Is that kind of how it happened?
I think Polars scratches some itches that are out there in the previous state of data frames in the world. I'm pretty opinionated of what a data frame library should do and shouldn't do. So I've been bugged by inconsistencies, non-strict behavior in pandas. In the past, it has cost me a lot of debugging time when silently data types fail into a pipeline, get an error 20 minutes in, and then you need to get that state back, or so everything works when your data set is small, and then you scale up to the production size and something breaks. And it always gave me a lot of headaches. And I really was interested in functional programming languages always, also a lot of side projects in those. And I really like the declarative style of functional programming, telling what you want. So that's instead of what you need. That's also what SQL does. If you read SQL, it explains you what you want as a result, or you explain what you want as a result, and don't tell the backend how to do it. So that's what I wanted in Polars. I want a declarative, readable API that if something goes wrong, it explodes in your face. And
better sooner rather than later, right?
Yes, yeah. And Rust is the same. Rust gives you the headache up front. So Rust just wouldn't compile. I really like those influences, like strictness, declarative, explode early, because if you think about your problem at the start, this will save you a lot of time and a lot of headaches later.
Which often people don't understand. So I'm guessing you gathered that when you moved from the data scientist to the data engineer element, that it's quite a common thing that there's something that works up front. And if only the data scientist knew things up front or better constraints, you would have saved everybody a lot of time. And you can bring that forward in programming in many fronts. Yeah.
Yeah, there's also, I feel that's your gatekeeper of functionality. There are a lot of feature requests where people want X to make this easier or that easier, where I think often you shouldn't. And another thing I didn't like about the world of data frames was that, say from PySpark or Spark, the other implementations seem to have been ignoring all the research in DataFrame or in databases. It's one of the most researched fields of software engineering, how to process data at scale and fast. But the DataFrame implementations I saw out there just executed the query like you wrote it. And we as users of data frames, we write terrible queries. We just read all columns. We do the filters at a position that's non-optimal. Yeah. And that's fine, because that's not our job. Our job is to write something that's semantically correct. We want to get a correct output. That's the job of the users. But we as data frame and database designers, we know how something can be fast. We should take that job from the user and ensure that something is efficient.
So maybe let me see if I got this straight. I think Polars, it's fair to say it's gone viral, right? So you see lots of articles, and that's a big kudos. But things don't go viral by chance, right? Usually, if it's just an incremental improvement, that catches some visionaries' attention, but not the world. I think you've caught the attention because you challenge the status quo. And I think you touched upon two things. I think it's significantly faster than Pandas, right? And that's maybe a standard many people live. So it's good that you challenge that. Maybe part of the reason is it was developed in Rust, but I don't think that's the only thing. You touched upon something very fundamental, is you're articulating that it's a data scientist or a senior data scientist who uses Pandas intuitively will know maybe I should drop the columns I don't need earlier versus keeping all the columns, doing my joins, and then dropping in the columns at the end. And I think you're saying that that's actually what database people have been doing since the beginning of time. Then you know that the order matters, and you can choose to tell what you want, but not how you want it. So is that kind of like a guiding philosophy that you applied here in Polars? Is, okay, dear data scientists, you want to get an insight? Let Polars figure out the right way of doing it. And you took all that knowledge from databases, so you put in a whole bunch of optimizations. Can you maybe give me a few examples of these optimizations, and how do you actually express that? Because I think that's the key thing here, right?
So the most important part of this is an API that allows this. We have to do this.
Not a problem.
So it starts at the front end, by having an API that allows us as a query engine writer, developer, to understand what the user intends. So initially we wanted to follow the Pandas API, but the Pandas API is eager, and eager means that if you ask it to do something, it does it immediately. But let's say I sort a data frame. I ask it to sort it. It will sort the whole data frame. And then I ask it to only return the first 100 rows, then I have sorted the whole data frame while I only would needed to. So I did a lot of work which wasn't needed. So with an eager API, you're not able to get a user's intent. You only get it on an per operation basis, but not on the whole query.
Right.
And if you are able to scan the whole query of a user, you're able to understand the intent of a user, and you can start reordering operations. You can, if you do a join or union and some files, some branches of this query plan, so you get a DAG of compute DAG of the operation you want to do, and if some parts of this tree read the same files, you can cache those reads or you can share the reads. You can do filters before you do a join, so you have less rows you have to join. You can select only the columns you need. So all this, you can push filters to the scan level, so you can filter directly while reading. If, for instance, in Parquet files, there are statistics in the header files, in the header informations of the Parquet files. And we can use those statistics together with the predicates. And the predicates are that's database jargon for instance, if column A is larger than 10, filter out this row. That's a predicate. And you can use those statistics, and therefore you potentially can skip whole files from reading. So this can have huge performance, but also memory implications. The other thing that was hard in the Pandas API is that it's idiomatic to use lambdas. So you have those assign method chaining, where you assign a column and then you say x equals lambda, and then you take another data frame column. But a lambda is opaque to us. A lambda is a function in Python. We don't know what happens inside of them. And anything can happen because Python isn't typed either. So we even cannot be sure about the types. So what we wanted was, what I was thinking is, why do users need lambdas? That feels like they want something they cannot express in the API, in the domain-specific language you give them. So that's why we came up with the expression API, which are very small building blocks of operations which can be chained. And every expression can be combined with another expression, and you can do this indefinitely. And by the combinatorial explosion of things you can combine, you get a very powerful API, and you can do a lot of things with expressions, Polars expressions, without ever needing a Python lambda. And this has a lot of benefit for a few reasons. One is that expressions are not opaque to the optimizer, so we can optimize them. They run on Polar's query engine, so they run super fast in Rust, and they are not blocked by the Python global interpreter log, so we can run them in parallel. And we actually do. Most expressions run embarrassingly parallel. There's a lot of parallelization going on.
I want to double click on a whole bunch of things there you said. So you made it sound like it's super easy, but it seems like you've actually hit on multiple things there. So maybe to pull that apart. So on one side, the parallelisms. Python per se is not really parallel, right? So it's got this async stuff, and it's not really parallel. It's a bit like a round robin. People think it's parallel, but it's not really. So true parallelism from a C programmer is a little bit different, right? With threads and you're locking variables. And I think that's where Rust also is a bit different. But yours and Pandas itself also is not parallel. The way it's built, to the best of my understanding, it leverages a lot of NumPy. It has to put everything in memory. But the architecture is actually not so easy to parallel things, right? So you can't like when you're doing a group by, if you're taking groups, it's not so easy to do the maths in parallel. But I think you can do that, right? Polar's query engine enables you to do parallelism. So that's one big speed up. You also said something there was the optimization. So your query planner. Tell me a little bit more about this query planner. Pretend I'm a data scientist. I don't know what a query planner is. Walk me through how, from my Python code using Polars, how does that end up being a query planner? What happens?
Yeah, we as Python developers are not really used to thinking about a query planner or a compiler in some sort, because Python until recently just ran the code as was. I believe it's doing some JIT optimization currently, and it's getting a bit faster. But if you program in Rust or in C, the compiler will optimize your code like super aggressively, and it will definitely not write it the way you have execute it the way you have written it. It will do all kinds of stuff. But we can do the same with data processing. The amount of work we need to do when processing data, we need to scan millions of rows, do joins, do group bys, go all over the plays. We do a lot of memory allocations and potentially have a lot of cache misses. There are naively computing the query would be a silly thing to do. So the first thing what we do is from the query a user writes, we construct a tree, a computation DAG. And this tree is often called a logical plan. And this logical plan, you can think of it as an AST in Python or in any language. The logical plan describes what operations you want to do. And it ends up with the result, and then it reverses to the input files. And if you have a join, then the tree will have two branches. And if you have multiple joins, you will have branches. If you have a union, you will have even more. And this tree, we will analyze this logical plan. We will analyze this logical plan, reorder operations, see if we can elide nodes. So if you're doing nested unions, we can flatten the unions. We combine filters, if you do multiple filters subsequently, for instance, if you would do a filter, then you would filter the data frame and then you materialize a whole new data frame and then you would do a filter again. We would combine those filters. We would push the filters to the scan level so that we don't need to materialize the rows. On the expression level, we do constant folding, which means that if you multiply by several constants, we can multiply the constants immediately without first multiplying the whole column with that constant and then materializing a new column and do it again, that kind of optimizations. But also if you do a sort followed by a head, we can swap that operation for a top K. And so there are a lot of subsequent operations that could be replaced by an operation that would be faster because it has more knowledge.
But those things are kind of things that go further or far beyond what a seasoned pandas programmer would do. So you could rewrite your panda code, right? The chain, you could do some of these things, and probably more senior panda programmers will pick up on these patterns and naturally do it. But the junior data scientist is just getting started, or in a Jupyter notebook, probably would never even think of these things, right? So you're kind of saying the junior data scientist is never going to get this. It's not their background, it's not their intent. So let's just do that for them, right?
Yeah, and there's also stuff we can do on the back end, which you never can do as a user. We know, for instance, that sometimes we don't have to do bound checks because we know that the tuples we produce are inbound. So we don't have to check every access. So we can be much more opinionated because we can be certain of things. So there are a lot of fast spots.
Okay, and the other thing that you also mentioned is the memory copies. Walk me through how does Polars actually deal better with memory? Because my understanding, and correct me if I'm wrong, is Pandas is built primarily on NumPy, right? And the NumPy implementation, it's like a C array, which I guess is not that different from PyArrow. But the way NumPy stores things is different to the way that Arrow does that. And when you do operations in Pandas, I feel, but maybe this isn't my understanding, you have to load everything in memory, and it's not so easy to split it up into chunks, and you don't really have control of where your data lands. So you don't have control on L1, L2, L3 kind of things. But in Polars, do you have more control over that? Is that also a part of an optimization on the memory?
So Pandas is indeed based on NumPy, and since 2.0 also on PyArrow. And they dispatch control to the implementations on the NumPy or PyArrows. And definitely operations in NumPy and PyArrow will, on that library side, they will ensure they do things cache efficiently. They're all good programmers there and things will be fast. But if you, for instance, use NumPy to implement your own, or PyArrow to implement your own algorithm, for instance, you will not reuse buffers. If you take a NumPy array and then you want to, I think everybody in Python has used NumPy to implement their own algorithm. Every new NumPy array you create is a new allocation. Going through the allocator is super expensive. These allocations cannot be reused, but we, on the back end, we have full control over the memory, over how we traverse caches. So every algorithm, we can save a lot of expensive allocations. We can ensure we traverse memory in a way that's cache efficient. We can elide bound checks, because also in NumPy you cannot elide bound checks. If you take by index, you have a bound check every time, because it would be unsafe to do. And that API should not be exposed to the Python world.
Oh, I see. So I didn't quite realize that. Okay, that's interesting. Yeah.
On the C+ and Rust side or C side, you have full control over memory and you can do a lot of tricks that can save a lot of expensive compute time. There's also inlining. If you do a group by, for instance, you produce 1 million groups, going to NumPy or PyArrow or another dynamic function that does the aggregation can be quite expensive. If you have an indirection from the function call to the code that executes it, it's not inline. Long story short, when you have full control on the query engine you write, you can look at every thing that might be a performance, that might have performance implications, and reassess how you do stuff. Do you use that function that lives somewhere else, or do you write it at that location and ensure that it is as fast as possible?
If I understand you correctly, so even with Pandas 2.0, right, so he enabled a different backend. So whether it be it NumPy or PyArrow, there's always going to be some kind of limitation because they don't control, Pandas by definition doesn't control the entire query. And part of the beauty of what you're saying is you can analyze the query up front, you can look at everything, and because of that, you can have optimizations kicking in that most individuals would never write themselves, could never write themselves, and you're taking the knowledge from database systems, compilers, which have historically done this. It's just applied at a different domain. And because of that, that's where you get all of these big improvements, be that speed, be that being able to do things in chunks. So often Pandas, if it doesn't fit in memory, people get very frustrated. Oh dear, it broke. Now what I do, and then how do I split it up? And if I understand that to do this, you wrote a specific API which was well thought out, which enabled you to do this, right? So you are alluding to that maybe people shouldn't be using numbers left and center. If you have an expressive way of describing what you want, you can actually cater for probably, 95% of all use cases. And that is where the big win is. Is that a fair summary to think about it like that?
Yes. I got two things I want to talk about here. One is the memory. Let me remind me of that one. And the other is another benefit of the expression API, in my opinion, is that we run this on a query engine, on an interpreter, and that has huge implications of consistency. We only have one interpreter, and it has to abide to rules, and we cannot sidetrack from those rules. So every expression abides to the same rules, and therefore the consistency of how our engine behaves is. Of Polars is super consistent in that regard. And if you understand how expressions behave, you can extrapolate that knowledge. And I think that's also another big benefit of our expression API. Before we had that, every operation was just implemented as a function on a series. But this allows for divergence in consistency super easily because it's just hard as a programmer to be consistent in everything you do, especially once the project gets larger, stuff gets implemented by different people. We use CI, we use linters, we use everything to control this consistency. And in Polars, we have an execution engine that also forces us to be consistent. So I think that's also a major win on the expression API. And on memory, so I think Pandas 2.0 going to arrow memory is super good for the Pandas project and makes a lot of sense. For numerical compute where you didn't have missing data, NumPy is great. NumPy is just as fast as arrow. It doesn't matter. But once we have missing data, there's not really a good way to represent that in NumPy. And once we have strings, the way Pandas stored strings in NumPy was terrible because the string is heap allocated somewhere else. And that means that on every axis, you have a pointer going to the string, so that's a cache miss, and then the string will be another pointer to the actually data of the string, so you have a double cache miss on every axis. Maybe even worse because you have a Python object surrounded by it, so maybe there are three. So in any case, it's terrible. So that problem has gone now.
NumPy was designed for numerical calculations. It wasn't designed for strings, right? Yeah.
No. So you could argue that NumPy was misused for this end. And on memory, I go back to the logical plan. So we have a logical plan of the tree we want to do in Polars, and then we can translate that logical plan to a physical plan. And the physical plan describes how we actually implements what we're gonna execute. And in Polars, we have two physical engines. We have two engines. One is the normal lazy engine, which needs to keep all data in memory. And the other is a streaming engine, where we don't take all the data in memory, but we stream the data in batches from disk. And then we push it through our engine pipeline. And in the end, we can materialize to a result, or we can also write it to disk immediately. So you can read from disk and stream to disk your results. And especially with that streaming to disk, you can process data sets that far exceed your RAM capabilities. And you're actually limited by the amount of storage you can store in your machine. You often also see some benchmarks where people profile memory usage, which I think doesn't make a lot of sense, because if you have all your data in memory and you profile memory usage, you should probably just use the streaming API. And in the streaming API, I think we should use as much memory as needed. I think that there's always a trade-off with compute performance and memory. And I think the goal should be not going out of memory, but ideally, I want Polars to use as much memory as possible without going out of memory. What we do during the streaming is we keep track of the used memory and try to change the strategy of what we do depending on the memory. If we go out of memory, we spill to disk. But I think benchmarking or profiling the memory usage and saying that the lower memory is better I don't think that's the proper benchmark, because I think not going out of memory is what's important.
That could be misleading indeed. So if you've got like a 16 gigabytes of RAM, if you say, oh, my program only uses 1 gigabyte, yeah, but if you used 10 and it was faster, then why was that such a bad decision anyway? So ideally, yeah.
You have it, let's use it.
Yeah, no, that's very cool about Polars. I think there are many things that you do use which are really great. But maybe to talk a little bit about the implementation, right? Polars is not a 1.0. So tell me a little bit about why is it not a 1.0?
We will be a 1.0 soon, because Semver tells you that you should be on 1.0 if it's production ready, and we are production ready. I have a bit of I don't like the expectations that this brings upon a developer. I think we will be on 2.0 very soon, because I think going for this backwards compatibility very stressfully, like hinging onto that, will lead to having a inferior product at the end. We make mistakes as developers, and we need to be able to correct them once in twice a year or something. And often those breaks are pretty small. I don't believe that semantic versioning really encapsulates this properly. Like the core of Polars and lazy, I think our API is very stable with the core things, but we are adding new functionality in a rapid pace, and this new functionality we are not entirely sure about.
Yeah.
And the semantic versioning is a number that represents the whole API and every operation and every behavior. And I think hinging too stressfully on that is bad. I think you should be able to add new functionality, and you should be able to be unsure about how this API should behave and what's the best. And getting this API out in the world gives you feedback on how it is used, what can be better. Yeah, insights change. And
So it's interesting you say that. I think Python as a language, it suffers a little bit from that, right? So the Python language, it doesn't want to go to the 2 to 3 was very painful for people. It puts a lot of stress on all the core developers. So anybody who builds a package, that I can feel that stress building up. And what effectively happens is there's many peps or many ideas, even on the Python language, how to make things better, but now you're held back all of a sudden for maybe the wrong reasons. So if I hear you, I don't want to be held back. If I know a better way, if I explore and I can get things better, that is better for everybody, right? And maybe we should embrace change and not fear it.
Not all change is the same. So if a method name changes, it can be fixed with a search and replace. It's
not a big deal.
So it's not that big of a deal. If you have good transition guides of how to upgrade, like not all change is the same. I think the Python 2.7 to 3 was a lot of change, and that can be disruptive. But yeah, removing deprecated functionality, which clearly were a bad idea, which are hindering improvement. Yeah, I think that should be removed once in a while. packages who actually do the same, but they hide it by not using semver, but using a version number that has the year in it. Postgres does this every year. I know it does this.
Yeah. Yeah, so indeed, maybe putting the 1.0 version is maybe putting too much on it. But
well,
then
we're going to it, but I make you the promise that we will be in 2.0 very soon.
Very good.
Yeah.
So you've mentioned that on how you develop Polar. So I think we spoke a little bit of where you came from, what's so special about it, and there's lots of good things there. But you also mentioned a couple of times that it was implemented in Rust. So can you maybe share a few words of what does your entire tool chain look like? And maybe can you go a little bit deeper of why you chose Rust over, I don't know, C++ in the first place?
Yeah, so I got into Rust because a friend of mine said, come Richie, join the hype train. And I thought, why, it's too low level, I don't need this, probably. I thought Rust was for systems engineering and I didn't see myself writing a kernel of some sort. But that's also mostly because I just wasn't that much, I didn't understand much about it yet. In any case, I followed him and there's a book, Writing an Interpreter in Go, it's a great book if you want to understand more about interpreters. And we took that book and worked on in Rust and learned a lot about it. And that sort of made me super interested in understanding more about low-level computing, about memory allocation, about performance, about cache hierarchies, etc. So that's how I got into Rust, and I really fell in love with Rust, with the strictness of it. I can recall the first time I tried to refactor something, I thought, man, this is so hard. Why doesn't it allow me to do this? And I thought, because some refactors can take, if you have a large project, it can take you a day and you drink a lot of coffee. But once you have had the experience a few times that after the 6 hours, the program compiles and it runs correctly. This is very important. It shows the strength of this super strict language, because in Rust, I now dare to do any refactor and I can trust it will work out in the end. Mm-hmm. And in Python, I wouldn't dare to do this because everything is runtime and Python would just run and we would have a lot of bugs in the end because it wouldn't. Well, things get better with MyPy and all those linters, but they're not obligatory, and that means it's as strong as the weakest link. If anything is not correct, then the whole program might not be correct.
And you don't often know that, right? So all the dependencies and all the libraries, that's sometimes quite invisible to the user, right? You import, 10 libraries and hoping that it's working well. And some of the most famous ones do it pretty well, but maybe not everyone is as strict. You can't guarantee stuff,
No, so that you can opt out of this strictness, that means you cannot trust it.
Yeah.
So that's how I got into Rust.
But maybe just as a question, so what is actually so different between Rust and C++? At a high level, can you break it down for me?
Yeah. On a machine level, they're all the same. They all compile to machine code and have the same performance characteristics in the end. Though C is as unsafe as it gets. It doesn't do any attempts to make things safe for you. And when you write a small program, things probably work. But once your program gets large and you start with multi-threading and race conditions and who owns which piece of memory and who needs to free it, things get the maintenance and correctness of this is too hard to put on the mental model of a programmer. I believe that on a survey, almost all bugs in Firefox, I don't know, I believe Microsoft did a survey on this, and most bugs were memory safety issues due to C and C++. C++ gets better because it has CII, resource allocation is instantiation, I believe it stands for that. Means that if you construct an object, a class, if it goes out of scope, it will be freed immediately. Rust has the same memory management. It doesn't have a garbage collector. C and C++ also don't have a garbage collector. It doesn't have a runtime. This means that the performance is very predictable. There will not be a stop the world garbage collection sweep. But different from C and C++, Rust comes with a borrow checker and a constrained memory model. So the borrow checker, there are a few rules in Rust, and that means that memory can be shared with everybody infinitely. Everybody can have a share of memory as long as they are not allowed to write to this memory. So I can get read access, but as long as one thread or one piece of code gets mutable access, nobody is allowed to have read access. So that means that memory mutable access cannot alias. So you cannot share pointers around and forget about them, because then Rust will not compile. So Rust will complain a lot if you do things that are probably a bad idea. So there are a lot of designs you cannot compile in Rust, but those designs are also super unsafe and probably wrong. You can make it work in Rust, but then you have to go down into unsafe, and unsafe means so you have safe Rust and unsafe Rust, and in unsafe Rust you say to the compiler, okay, trust me, I know what I'm doing. From now on, I only work with pointers which have no guarantees.
Interesting.
But those parts in Rust are when you opt into unsafe, it's very clear. You tag it, okay, I opt into unsafe. You put comments about the assumptions you make here, about the invariants you use, and the amount of unsafe. For instance, in the Polars code base, we use unsafe for performance reasons, but I don't know in percentages, but most of the code is safe. Whereas if you would write C or C++, the whole code base is unsafe because there's no checking whatsoever.
Yeah, so it's funny you say that, because I remember my university days, I learned C, and there was this course about threads and safety and race conditions, and it was almost like a rite of passage to be able to find race conditions. It was like defining how smart you were as an individual, and the professor was always very happy of writing this really funky code, and there was an error there, and it took all of us, as 30, 40 of us, super smart people, very passionate about it, scratching our heads, trying to figure out things and trying to prove it wrong. But it feels like that's just generally the wrong approach. That's a waste of precious cycles of these 30 people, including the professors. Maybe we should write a language which prevents that. And I think that's where Rust is coming in. Is that kind of the idea?
This is how Rust has originated. Firefox tried to rewrite their engine to multi-threading. They were writing a concurrent engine, and they tried it in C++, and I believe they failed 3 times.
Wow.
And they put a lot of effort in it with a lot of smart people.
Yeah.
Eventually, they were able to do it with Rust. Rust was designed in Firefox initially, I think 12 years ago or something. But the borrow checker, so this constraint that you cannot share mutable memory with multiple pieces on multiple places, this also turns out to work really good with constraints of concurrency.
Yeah. But that's just the Rust part. So if I understand correctly, Polars, and I'm taking a leap here, Polars, RS, the Rust, that's where it comes from. But most of the code is written in Rust. Walk me through a little bit of what your toolchain looks like.
Yeah, I think Polars is, at the core, we are adhering to the Arrow memory specification. So we use the Arrow 2 implementation for that.
Okay.
And we use some compute and I/O from that grade, but almost all compute and also a lot of I/O is written by Polars itself. And we have full control over the memories. Yeah, so that's the fundamentals. Then we go into the Polars compute, more low level, where we implement things like arithmetic and comparisons and base operations. And then we get into the more high order operations like joins and group bys. And this is all in Polars core. Then we have one abstraction higher where we are in Polars lazy, where we have the expressions and the API and also the query engines, which are built of more Polars core constructs. That's all on the Rust side, but we go to Python with a wonderful crate which is called Pyo3, Pyoxide, I think. Maybe it's called Pyoxide. Probably it's Pyoxide. And you write it as Pyo3, and this is an interface that makes it really easy to expose your Rust structs and methods to Python and interact with the Python GIL and Python objects, etc. Great shout out to that library. And on the Python side, everything is just duct tape. The Python is a mere wrapper around the Polars query engine, and similar to how NumPy is this. Yeah. So I think sometimes I read this and I wonder if people think that it feels unPythonic because of this, but we actually try to be super Pythonic. We use Python exceptions. It should feel as Pythonic as NumPy, which also is just a small wrapper around their C interfaces.
Yeah. It's funny if people say that. So people always say, oh, Python, but actually most of the most popular Python libraries are not actually written in Python. It's a bit of an ironic world itself, that the usability is and the ecosystem's there. And but just maybe as a curiosity, so how about testing in Rust? From my Python programming world, testing is really important, and I use a lot of PyTest. And part of the reason why testing is so important is it's a bit of the typing. You can't guarantee things, so you end up writing a lot more tests to validate things, and then your test code becomes bigger. And not everyone realizes or does a good job of that, but once you get there, you do it and it becomes a habit. And what about the Rust side of things? Do you also have a similar issue, or is because of the compiler it reduces on the testing, or how strict are you? Walk me through a little bit about that.
Yeah, so type checking isn't needed. That's guaranteed by the compiler, by the Rust compiler. So we don't have to check any types. Otherwise, just the code wouldn't compile. So that one is off the table. That's easy. But yeah, testing is super important. I think it's one of the most valuable things in our code base. Having a great test suite allows you to do a lot of refactors and ensure that what you changed still works as you expected it when you initially wrote it. We test a lot. We have a lot of tests, but we test mainly, we have tests in Rust. But testing in Rust takes a lot of our CI cycles. The CI is very expensive because the Rust tests are compiled to a single binary per test module, I believe. So it takes a lot of time to compile. So instead, what we do is we do most of the tests in Python, because then we only need to compile the Python library once, and then we can run all the tests at once. And it's also the perfect integration test.
Right.
So we do most of the tests on the Python side. Yeah.
Yeah. How do you actually choose what a new feature is? And can you walk me through it? So, you've got all these users. I'm assuming you get requests left, right, and center. How do you actually prioritize what's coming? And maybe a second thing, is there anything particularly exciting that's coming up in Polars that you would like to share?
Yeah. So a feature must just fit into the model of what I want Polars to be. It should fit a query engine, should fit a DataFrame interface. Like if you come for a feature that better fits a tensor library, then I'd say probably convert to a tensor first and then do that operation. It should make sense. Yeah, it's quite opinionated. Priority is mostly by who has spare time to implement it and how much of a need this is. Luckily, we're at the position now that this much of a need is very low. We are pretty feature complete already. You can do a lot. And most feature requests are more niceties, nice to haves, than I cannot solve this in Polars. But what I think the DataFrame world really is lacking is processing larger data sets. That's where my focus is completely with Polars. I want to make the streaming API as complete as possible. So that's my full focus this year. And I want to be able to, users should be able to process a 300 gigabyte data set on their laptop. I don't want to get into a cluster when I get a big data set. We get super powerful machines. I've got a CPU with 16 cores. Yeah, let's use the thing. And I think we shouldn't be limited by our RAM size. So that's the most important thing at the moment. But luckily, the open source team is getting larger, and we get a lot of features that fit the Polars philosophy because people take up their own specialities. And yeah, there are people who are, for instance, Marco is super knowledgeable about date times and all the edge cases involved. And I'm really glad I don't have to do anything about this. And we can get this help out of the open source community.
Yeah, because I think I saw on GitHub you've got like 200 contributors. So you've got a wide variety of people helping you out. So that's very nice. But then it becomes a bit of you as the author need to steer the ship a little bit more, right? So I'm assuming you, as time progresses, you spend more time setting a vision or guidelines of where you want things to go than actually maybe implementing it yourself. As maybe that changed a little bit since that side project that started a few years ago. Do you have guidelines for developers? Or maybe I should ask it in a different way. Is if you need help, what do you tell new people to say, hey, help me with this? How do you ramp these people up and bring them up to helping Polars go in the direction you want?
So I'm not the best at that part because it takes a lot of time getting new people into. So I think the community is doing it. We have a Discord, which is really active, and people are really helping each other. And we core developers of Polars, those are just people who do this in their free time. And initially it started with feature requests, or they started doing some small gripes they wanted fixed. And we just get different specialities. And by all the Discord we have on the GitHub issues, I really trust that the team understands the vision of Polars. They own the same vision currently. And so I think we keep each other sharp on how we keep things consistent, how things should work, and we all have our own specialities and people work on their specialities.
Right.
I feel this flows naturally by the amount of discussions we had on GitHub issues.
Yeah. So then maybe just to clarify, so if someone wants to get started and helping you out, what's the right way of doing it? Is to jump on the Discord? Is it to create an issue? Is it to communicate with you directly via email?
I always appreciate it if you open an issue and say you want to do this and first start to have a discussion if we want this. It's a bit annoying for both parties if there is a 40 files changed PR open and we don't want it and you put all the effort in. It's good for nobody. Please open an issue, start a discussion, and we can help you out. We can point to places where this probably needed.
Or other things. So that's the other thing. Sometimes someone opens an issue, they start doing it, and then it doesn't get used. But if you say, hey, I want to do this, you can say, oh, if you could do that, actually, I would prefer it if you did this. And if you did this, I can guarantee it gets in much quicker. And then everybody's winning. And you feel like you're working together as a team, right?
That's what I meant with start the discussion.
Yeah.
Make sure we align first before the effort goes in. And we had a lot of community help for doc strings and types. And there are also the easy things to get started. Just more examples and more.
Yeah, because your documentation is pretty cool. So how do you build it? What's behind your documentation?
Which one? The reference?
The reference guide. It looks pretty slick. You build it out? Is it?
All the credits to the Pandas team here. So we initially just took their Sphinx, and that's how it started. But we changed it. Initially I didn't want to do Sphinx. I don't find it intuitive, but it takes a long time to set up. But once it's set up, you're happy with it, and the maintenance is pretty low. But the initial setup is
painful. Yeah.
But again, we started with the Pandas theme and adapted it to Polars, and later Alexander Beatty added a lot of cool features, cool drop-down menus, and a lot of community effort. A lot of doc strings are just added by people.
Yeah, well, that's a nice way to get going, right? So often if you're not sure how to get going, you look at the documentation, make it better. It forces you to read things, and that's the way that often people get engaged in projects.
The documentation is super important, and on the Rust side, we are not nearly at a level that's acceptable, but the community hasn't helped that much on that side. And my priorities go into making Polars better. But I hope we can one day have a really good Rust documentation as well.
Just out of curiosity, currently you have a Rust and a Python API for this, right? But are you envisioning that it bridges into other languages? I don't know, like Julia, I don't know, Java, whatever. Is that the?
It already does. We have a Node.js implementation.
Okay.
We have a R implementation. Those are both community driven. They are under the Polars namespace under the Polars repo. Done by two developers who just put a lot of effort in getting the front end on top of Polars.
Nice.
And so R and Node.js, and there's a Ruby implementation outside of the Polars project done by someone.
Nice. But that's not where your focus is. So you said your focus is really to get this running on scaling it up. So 300 gigabytes, Polars is going to eat this for breakfast. There you go.
Yes, that's the focus. I think that's the niche that really can do better.
This is a great place to stop this episode. I hope it triggered your curiosity in some shape or form around how MATLAB, Python, or Julia are actually used in the real world. If you did find it interesting, just subscribe in your favorite podcast player and write a review. This will help the podcast keep going strong. In addition to that, don't be shy, share it with a couple of friends, as who knows, one of them might be a future guest on Inspiring Computing.